Hello, everybody, and many thanks, Christian and Thomas, for inviting me to tell this short story during this 24-hour-long memorial event for Eric Grimm, who was a friend and a great scientist who's actually deeply missed, but whose contributions to paleoecology have been quite remarkable. And among the many things that I appreciated of Eric was that his efforts were actually focused on providing tools that were meant to be for the benefit of all, including, for instance, paleoecological databases. And so in the following, I'll tell a short story describing how we, a group of people, used one such database to explore the long-term emergence of biological novelty. And this project was actually a follow-up project of what Thomas just briefly, or actually introduced earlier on. Now, let me first give you some background information on what actually ecological novelty means and how it emerges and what are the supposed causes for its emergence. The idea is that during the past decades, there has been growing concern that ecological novelty may arise in the future. The main assumption being that the emergence of novelty is an inevitable consequence of individualistic species responses and environmental alteration, which include, for instance, the emergence of abiotic novelty in climate, for instance, high rates of environmental change, and human activities. Now, to start off, different mechanisms have been proposed for the emergence of biotic novelty due to the appearance of abiotic climate novelty, for instance. These include, for instance, the observations that parts of the modern climate space, which is here depicted in blue, may disappear, and currently unavailable portions of the climate space, here shown in yellow, may unfold. And therefore, species that lack a pre-adaptation to such abiotic novelty in climate conditions may be potentially at risk in the future. And another issue concerns the rates of climate change that could cause biological novelty if the suitable climate space shifts across the landscape faster than the species can follow the shift. So this latter point is actually quite relevant, given that the recent increase in rates of radiative forcing largely exceeds the rates of change of any previous episode of the past 20,000 years, and that rates of climate change will likely be high in the coming decades. Now, what does actually novelty mean, or how is it measured? Now, to put it simply, novelty represents community-level changes across sites. So instead of looking at just how one taxon moved across the landscape, we look at how the communities move and displace themselves, and how the communities change through time and in space. So novelty can be quantified as the degree of dissimilarity to the nearest counterpart, which is a concept that is very similar to the non-analog concept. However, the large majority of studies attempting to reconstruct the image of novelty are quite limited to relatively short time periods, typically no longer than a few centuries. And therefore, the long-term development of novelty is currently, or was currently, weakly constrained, actually still is, despite this study. Now, in addition to being an important concern for ecological management and restoration, the concerns arise as to how novelty will develop in the future. Well, Steve Jackson suggested few scenarios in one of his seminal papers that was titled "Novelty is Not New." And he posed critical questions, including as to whether novelty always increases and how it increases, how it is related to rates of environmental change, and what's the influence of human agency? Can it accelerate the rise of novelty or not? Or how much? And so we address these questions changing a little bit Jackson's conceptual framework, which was focused on modern to future. And we just modified the x-axis and said, okay, let's take any time in the past and see how novelty developed with respect to that any time in the past in its contingent futures. So in other words, we took a viewpoint that was similar to the one used by Jack Williams, who posed himself as an Ice Age ecologist. So for this study, we used the European pollen database and collated the data into 500-year wide time slices. And we quantified both novelty and rates of change for subsequent time intervals. And the two measures are actually measured using the same dissimilarity metrics, but are therefore comparable. However, they differ because novelty quantifies the change across sites, whereas rates of change quantifies the change within site through time. And so we use the rates of change as a proxy for environmental change at the site. And in addition, we use the difference North Grip Delta 18O record as a proxy for climate change over entire Europe, which is a very simplified approach, but that's what we did. Now, similar to results obtained earlier by, for instance, Brian Huntley or Alistair Seddon, rates of change were high at times of higher climatic change, for instance, during the deglaciation. And the increase in rates of vegetation change during the late Holocene were attributed by us to increasing human pressure on the landscape, which transformed vegetation assemblages. And when comparing the rates of change to novelty, we noted that we noted a few things. Now, first, the higher rates of change actually occur at times when the displacement distance of the vegetation communities was highest, which is an indication that rates of change were linked to the spread of taxa across Europe. And surprisingly, however, novelty values were very low and were generally smaller than rates of change. And this, we thought, might suggest that the spread of taxa helped reducing the emergence of novelty. And then we looked at the spatial distribution of rates of change and novelty values at different time periods, and noted that the ecosystems at higher latitudes were less prone to encounter higher novelty. And interestingly, this pattern is consistent with modeled novelty in abiotic factors for projected climatic conditions. And therefore, we thought this supports the idea that high latitudes are less prone to encounter higher novelty in the future, which is an interesting result, I believe. We then analyzed a longer-term trajectory of novelty by comparing iteratively each reference system to the target systems in their future. And we came up with this, I think, beautiful plot showing that novelty is generally increasing the further we move away from the baseline. And however, the emergence of novelty was not homogeneous and was baseline specific, which poses questions as to where do we put our baseline today to measure novelty in the future. Nevertheless, interestingly, we found that novelty emerged faster in recent millennia as can be seen by darker colors in the upper right corner of this figure, which suggests that human actions accelerated the rise of novelty. Now, there's quite some evidence of the emergence of novelty on land. And our study just contributed to a small portion, but looking at long term. But in marine systems, there is very few or actually no data at all. One point is that databases are very short, but nevertheless, exploitation of marine environments and resources has been rising over the past decades to such an extent that people talk about the idea of a blue acceleration for marine systems. And there's the idea that novel combinations of physical or oceanographic conditions are not unlikely. And these may affect ecosystems in addition to anthropogenic impacts of eutrophication, fisheries exploitation, and other factors. So building on these premises, there's one study that appeared recently that used a database for the Baltic Sea that covers about 35 years only. And this study looked at how novelty in the different basins developed over this short time period. And today in the Baltic Sea, the north-south gradients of salinity and temperature shape species distributions, and thereby they determine the biotic community structure in the basins. And this study found that novelty of phytoplankton, for instance, is negatively affected by salinity, which suggests that basins with lower salinity in the north are more prone to develop novel phytoplankton assemblages. And further, spring surface temperature also appeared as a significant predictor for zooplankton novelty. Hence, salinity and temperature, which were identified as main contributors to high abiotic novelty, may be also important drivers of biotic novelty in this huge marine system. And maybe they might be also important drivers of biotic novelty in other marine ecosystems. So, as I said at the beginning, these were just two case studies showing a bit the added value databases can have. And clearly, all those who set up, maintained, and contributed to the databases and to these studies, as well as to follow-up studies like Jack and Kevin, are warmly thanked. And most of all, I'm thankful to Eric for setting up and for leading, in a way, the setup of the European Pole database and all paleoecological databases that are useful for our studies. Thanks.